Thanks, Sebastian. Thanks everyone for attending. We're going to talk about a program that we've been working on for some time. The command line program is called PyDarwin. It's an all Python solution for doing model searches in non-mem, model selection searches. And there's the website to download. Is open source. Do whatever you want with it, including modify it, use it, and it was developed on a grant in collaboration with the FDA. The FDA had a lot of input into this. It's a collaboration with some folks in the biometrics group, as well as the Office of Generic Drugs, who have an interest in developing some robust model selection methods. And we think it is robust. We think it is a completely general solution. The PyDarwin, the command line version, anything you can imagine doing in non-mem, you can search for. And by search, we mean try different hypotheses, test different hypotheses across a whole range of things that people typically look for in non-mem models. Compartments, absorption models, covariates, residual error models, between subject variability, inter-occasion variability, all sorts of, from anything that you can think of, you can do in non-mem, you can search for. We currently have 6 algorithms that can be used for the model search, starting with the exhaustive search, which we'll explain in a minute, is probably not the most practical solution. But you can look at every possible combination of compartments and covariates and residual error models, and again, everything else. But that isn't usually the solution that you want, because the computational load is enormous, as we'll see. So there are some discrete search algorithms that we've built into this, including Bayesian optimization and random forest with gradient boosting, genetic algorithm, and particle swarm optimization. We're not the first to think about how one would come up with automated methods for doing model selection. The standard one that probably most of us have used is stepwise covariate modeling in the package out of Uppsala PSN. There's also another older program called Wald approximation by Ken Kowalski and his group. A new one, Cove Search, in Uppsala's latest package called PharmPy, and a whole selection of newer AI machine learning methods to look at just covariates, to take various post hoc estimates and sort through them, looking for candidate relationships between covariates and models. All the ones we've listed so far are limited to covariates. That's typically what has been done historically. You come up with the basic structural model and the between subject variability terms, and then you search for covariates using those from those models, your current base model. Ours is more general. You can look at anything you want, not limited to covariates, but there are others. There's one other that is not limited to covariates, and that is the automated model development. Also in the Uppsala package on PharmPy. But the big question is why are we doing this? The FDA's interest, frankly, is more about objectivity, about not having any user bias for what should go in the models and prior assumptions about whether there should be a race effect or a 2-compartment model or anything else. From the user perspective, the main advantage of it is more efficient. It's not as tedious. When we develop budgets for model search, for model development, typically about 1/3 of the budget is for the model development, and about 1/3 for data set development, and about 1/3 for reporting. This dramatically reduces that time for the model search. Still need a data set, still need to write a report, although, as you'll see, we have some help with that. But it is significantly more efficient. It also is more robust. We've demonstrated this more robust. It is better than humans in finding a model that meets the numerical criteria. Again, limited numerical criteria. The search is based on strictly objective numerical measures of how good the model is. Still requires user input into whether this model makes sense and whether the plots look good. And finally, it is objective. That is a key concern of the regulators, is that there's not user bias introduced in the model selection algorithm. But specifically, why PyDarwin? Because it's not limited to covariates. It is a true global search. Compartments, error models, initial estimates, anything else you can imagine. More efficient, more robust. We're usually concerned about objectivity. But in sort of the big picture, it really provides a practical solution to examining the whole problem space, not just picking a structural model, two-compartment first-order absorption, because it looks good, and then going down some fairly limited path about what we might add to that model. It is a global search. It looks at all possible, it searches the space of all possible combinations of all of these characteristics, allowing you to do things that you can't practically do. You can't develop sort of the full between subject variability model and the full absorption model and the full covariant model for 1 and 2 and 3 compartment models manually, but you can do that with an automated method. To start with any search problem, you need to think about what's called the search space. And all algorithms require the definition of this model search space, including doing it manually. Even though we don't do this explicitly when we do it manually, we have an idea of what we're looking for. We start out, we write an analysis plan. The analysis plan says we'll look at 1 and 2 and 3 compartment models with first order and Michaelis-Menten elimination and these different absorption models. The difference is for this, you have to explicitly make that list. And then that model space is searched. And the searching of that parameter space is in many ways fairly analogous to what non-mem or any of the parameter estimation algorithms use to search the parameter space. On the left is a diagram of a simple two-dimensional parameter space with volume on the x-axis and clearance on the y-axis, and then minus twice the log likelihood on the vertical axis. And you're looking for the minimum point. You're looking for the value, the unique values of clearance and volume that give the minimum value of the objective function, somewhere right in here. The analogy in looking for a model and searching a model search space is the same. On the right is a two-dimensional model structure search space with a number of compartments on the x-axis and the elimination route mechanism on the y-axis. The important difference is this is a discrete model space. There's no 1.34 compartment model. It's 1 or 2 or 3. And similarly for the elimination mechanism, they're discrete values. And so you don't have any intermediate values, and this requires a different algorithm to search this. The standard methods in non-mem and other algorithms use a derivative. They take the derivative and they find out which way it's down, and then they move in the down direction until it stops getting better. Not an option for discrete search space, so different algorithms are required. There is no derivative, so the algorithms have to be different. But again, we're looking for the optimal combination of exactly one value in each dimension. Dimensions might include the number of compartments, 1 or 2 or 3, the elimination mechanism, linear or Michaelis-Menten or target-mediated drug disposition, the absorption models, linear, zero-order transit compartments with or without a lag time, or the different covariates, residual error models, omega structures, whether there are between subject variability terms, and I think an often overlooked model parameter is initial estimates. I think we don't do that enough, and that's one of the advantages of this is it facilitates searching across different initial estimates for parameters. Well, you put together that search space, that 1, 2, 3, 4, 5, 6, 7, 8, 9, 8-dimensional search space, 3 options for compartments, 3 options for elimination mechanism, etc. You end up with 700,000 possible models. Not something we're going to run. So we need a better algorithm for searching this. The search algorithms, all of the search algorithms, have a representation of the candidate models in the search space that is basically just a string. And there's a number of different representations, but in the case of a genetic algorithm, it's a bit string. And that bit string is divided up into genes. Specifically, in this case, the first gene is a number of compartments and includes 2 bits. In this case, you see the 0 and 1 as the first 2 bits. And those 2 bits get translated into a number of compartments. For example, if it's 0, 0, that's a 1-compartment model. If it's 0, 1, that's a 2-compartment model specified as microconstants. If it's 1, 0, that's a 2-compartment model with clearances, and 1, 1 is a 2-compartment model with clearance and V2. That specification of the structural model, number of compartments, then gets translated into a non-random control file, which is then compiled and run. And you get from that numerical outcomes that can then be used to say, is this a good model, or is it a better model than others, which then feeds back to the selection process, which then redefines the bit string that specifies the model. And this is all handled under the covers by PyDarwin. The user doesn't have to do any of it. They don't have to worry about the bits specifically. They just have to define the different values in the search space, the different dimensions, and what are the different options in each of those dimensions. And you can see here that there's a gene for number of compartments, and a gene for the relationship between weight and clearance, and one for the relationship between age and clearance, etc. And we spent a long time looking at this, and we quickly realized that all these algorithms are global search algorithms. And the global search algorithms are very good at searching for generally good regions in the sort of the full search space. Humans do a local search where they make one change at a time and then evaluate whether that one change makes the model better or not. And that's a very efficient algorithm. That actually is the most efficient algorithm as measured by how long it takes for the model to converge, the search to converge. But it's not very robust. On the other hand, the global search algorithms are very good at finding generally good models, but quite bad at making that one or two last changes that give you the best model in a little local area. All these algorithms have assumptions. We talked briefly about the genetic algorithm, but the Bayesian optimization, for example, assumes that the search space represents a multivariate probability distribution that is smooth, and that's not the case. And all of these assumptions are sort of generally true across the whole search space, but locally they deviate from this assumption. The objective function of the fitness function is not smooth locally, and so it's a violation of this assumption. And that means that we have to find some other algorithm to supplement this for local search. For example, specifically, genetic algorithm is very good at looking at the entire search space, finding generally good models, but to find that one last change from a exponential relationship between weight and volume to a power relationship, they're very bad at that. They're not very efficient at finding that one final change that makes the best possible model. So we found that all these algorithms can be supplemented with a local search that in some ways looks much like what humans do. It makes one change at a time and then looks at whether that change made the model better. We do this one change at a time, but we also do it two changes at a time. We found that that's also important, that the inconsistency of the local search space, in fact, is not downhill. Makes looking at all possible 2-bit changes necessary. And more about this later, but we think we have, with this combination of a general algorithm, search algorithm, supplemented by a 1-bit downhill search, one change at a time, and then followed by a 2-bit, two changes at a time, all possible combinations, ends up with a very robust search algorithm. Which brings us to the question of what constitutes a good model. Again, this is strictly numerical search. There's no subjective evaluation of whether this makes sense, whether the plots look good. That's something that the user will have to do before and after the model search. But the search criteria used is very general. It's user-defined. It starts with minus twice the log likelihood, and then adds user-defined penalties to that. We generally use a parsimony penalty, a penalty for estimated parameters, specifically 3.84 points if it is a hierarchical model for 1 degree of freedom. User can define whether they want 3.84 or some other number. We commonly use 10 points. We generally like models that converge, and so you can add a penalty if the model fails to converge. Some debate about whether a covariance step is an indication of a good model or not. So you can include a penalty if it fails to do a covariance step, and a correlation step, and a condition number. And then finally, you can include user-defined R code, where it will run some R or Python code after every model and calculate some additional penalties. That can be either things pulled from the non-mem output, relative standard errors, post-hoc A to P values, or you can run simulation and do a posterior predictive check or anything else that you want to do. And that turns out to be a very important addition to getting the model to behave the way you want it to. Very relevant for the Office of Generic Drugs. In that case, we want the model to adequately capture Cmax, for example. We're not very good at coming up with numerical criteria for capturing Cmax, and so we can actually do a posterior predictive check and see if the model adequately captures the Cmax. The problem with the command line is that it's really pretty complicated. There are several files required that it uses. The first is called a template file, which on the left looks a lot like a non-mem control file, except there are these little text snippets surrounded by curly braces that we call tokens. The complicated file is the tokens file, where it provides specific text to be dropped into the template file to specify non-mem control file, to specify the model. Is it admin 1 or is it admin 2 in this case? And this tokens file is complicated and unforgiving. It's a JSON formatted file. All these curly braces and quotation marks and colons and square braces and commas all have to be in the right place. It ignores white space, which means that, for example, if you want a new line, which you do in non-mem, you have to explicitly put in a \n to get a new line. Not very user-friendly at all. And so Certara committed to developing a pretty nice graphical user interface because the computer is very good at writing JSON files. All you have to do is provide it what you want, and it will write a JSON file. And that's mostly what we're going to talk about here. This is included in the new version of PyDarwin, has some new features. Probably the most important new feature is support for another parameter estimation engine, NLME, which has access to an R package called RSpeaks NLME that you'll be hearing more about. We think that's a very exciting new option for managing the model development, the workflow, the report generation, the archiving, the whole workflow of the model development and reporting and regulatory submission process. And you'll be hearing more about that. And it's built into the NLME component. It's easier to do that because non-mem being a freestanding command line application has some challenges in how one actually interacts with it. But NLME is owned by Certara, and we can access whatever we want with it and make a very user-friendly, streamlined workflow process around that. We did just get published a tutorial on PyDarwin, not Pirana with Darwin, but this was just in the December 3rd online publication, a machine learning enhanced automated nonlinear mixed effect model selection tool. Encourage you to look it up. It's I think it's going to be open access. We can get that done. It isn't yet. Last time I looked, it wasn't yet, but it will be open access in Conform Therapeutics. So mostly we're talking about and demonstrating Darwin in Pirana. Again, PyDarwin is open source, command line, not easy to use with these large, complex, rigidly formatted text files. Darwin in Pirana provides a nice graphical interface, checkbox, drop-down boxes to specify most things that you want. It's sort of comparable to, for those of you who've been around for a long time, the NMTran, creating the required files for non-mem. Pre-NMTran, which was in the early 80s, you had to write the Fortran code to run non-mem, and NMTran greatly simplified that, and that's what Darwin and Pirana does. It greatly simplifies the generation of these three files that are needed to run PyDarwin, as well as tools for generation of report shell, key models, user-defined plots, tables, and appendices that you'll see. So this is the second version of Darwin in Pirana. And it has been enhanced, so now it's all a JavaScript application, which again will facilitate further development of this and further streamlining of the workflow. But it basically looks like this. There's drop-down boxes. There are boxes for initial estimates for all the covariate relationships that you want. A very user-friendly checkbox, drop-down boxes. And just very briefly, when you're done, there is a new tool called Darwin Reporter that generates important diagnostic plots. We'll be showing that briefly, and James will be going through that generate plots that we typically include in reports, as well as some new plots describing the convergence and how well the model behaved. BPC, built-in BPC, again, drop-down menu, checkbox BPC to generate BPC plots. That is where I'm going to stop for the moment. I'll take any questions briefly, and before I go into a demonstration of Darwin and Pirana. Any questions about this so far?
Yeah. Oh, go ahead, Sebastian. You can pose it.
Okay, cool. Yes, there was one question that came through, and the question is: would you please explain more about parsimony for selection of a good model?
Yes. Typically, one of the goals in any model development, not just pharmacokinetics, POP-PK, is parsimony. Generally, any model, as it gets bigger, will describe the data better, and you end up you ignore how complex the model is. You end up with an enormous model, overfit model. Most of the parameters are you're modeling just noise, and so there typically is a benefit to simpler models. Famous quotes: "Make models as simple as possible, but not too simple." It increases statistical robustness, and so we typically include a penalty for each estimated parameter, theta at least, and for a log likelihood ratio test, a formal test of hypothesis for parsimony, we add a penalty of 3.84 points to the minus twice log likelihood for every estimated parameter. And that's carried on into this, except you're not restricted to doing 3.84 points. You can do anything you want. If you want a particularly parsimonious model, a fairly simple model for whatever reason, you might make that penalty large. If you only want to do sort of formal hypothesis testing at p equals 0.5, you might make that penalty 3.84. And that's sort of the most basic penalty that we add to the minus twice log likelihood for the model selection. If you don't do that, you'll end up with an enormous model, because bigger models always fit better, but you're mostly modeling noise.
All right, great. Yeah, thanks for that answer, Mark. And there's another question to your first input here in the first minutes. And the question is this applicable also for parent metabolite models?
It's not built into Darwin and Pirana. In general, yes. In PyDarwin, absolutely. You can do, again, you can do anything you want, anything you can imagine. PK/PD models, logistic regression, any of the algorithms, really, literally anything that you want. We have occasionally come across things that you can't do, and so we went back and built it in. The one thing you can't do right now is mu referencing, but we have that's in development. That will be the next version, to be able to do mu referencing. Other than that, you can do anything you can think of in PyDarwin.
All right, great. Yeah, and very interactive audience here. So we have another question.
I think it's the last question one time.
Yeah, so the question is basically, where do you see this technology in 5 years, and what do you think would be the value add?
We see this as being and there are other tools on the way that you'll be hearing about, but frankly, we see this as being the industry standard. The real limitation at this point is compute power, but there are obviously solutions to getting as much compute power as you could possibly ever want. And we're looking into making those solutions available. And there's no question it's more efficient, more robust, more objective. And the only issue is how long does it take? And if you don't have adequate compute power, these algorithms are dumb. Frankly, they're dumb compared to people. They're not as efficient as people at coming to the final solution. We commonly will run several thousand non-mem models to come up with a solution. If you're running it on an 8-core machine, that's not going to be practical. That's going to take weeks. What we need to do is to provide more compute power. And so that's what we see. We see this becoming one of the industry standard tools, maybe not the industry standard. We see it expanding into NLME. We think we can make some really nice tools on NLME to use this, and then access and providing tools to access more compute power. Compute power is cheap. Compute power on Amazon is 7 cents a CPU hour, a lot less than the people on this call are billing at. And so you're much better trading buying compute power and trading that for human effort.
All right. Yeah. Thanks.
I wanted to point out there as well, Mark, that around compute power, right? So PyDarwin and Darwin and Pirana both have the ability to be run on a grid workload manager, so in your remote Linux host. So certainly you can leverage the existing utilities in Pirana, such as the job cluster monitor, and execute Darwin more efficiently by leveraging additional resources, compute resources.
All right. Yeah. Thanks for that comment, James. Guys, we have 2 more questions. Do we want to take them now, or do we save it for later? How we are time-wise? What do you think?
Let's save them for later.
We save them for later, and now this is James's part, right?
No, and I'm going to do one model selection, and then James is going to do the reporter.
Yep.
Okay. So can you see Pirana now? I think you should.
Yes,
good.
We do.
Okay. So this is Pirana. I need to make some space here. We're going to start by making a new model, specifically a Pirana model. And this is the new interface. So if you saw Darwin and Pirana before, you see that there was a different interface. This is now JavaScript, which is going to greatly facilitate the development of new tools and for managing this process. But this is the interface, and you start with the data set, and we're going to start by, that's not the one I want, this one. Just grabbing the data set. There's a data set, and there's some automated definition of the variables, but we're going to add weight and creatinine clearance as continuous variables and sex as a, I can get to it as a categorical variable. And here's where we start to define the structural model. And we're going to look at advan 2, 1 compartment, and advan 4. In the interest of time, we're not going to look at a 3-compartment model. And we're going to include all of the covariates that we included as options for covariance relationships. And so we have advan 2 and advan 4 here. We need to start by providing initial estimates and saying what the search space is. Clearance, K, and volume are required. So those are all listed as present here. Present means they are there in every single model. But absorption lag time is not required by advan 2. And so we have the options of not having it at all in any of the models. It's not
I think we lost Mark for a second. James, are you on?
Yeah, I'm on. I can see Mark's screen. I think Mark's still on. And
I can't see Mark. Yes, he's doing stuff, right? But we can't hear his voice. Mark, can you hear us? apologies for the technical difficulties we experience here, ladies and gentlemen. We are trying to find a solution with Mark, but he doesn't seem to hear us. So we can maybe, yes. But please give it another minute for Mark to fix this problem. Otherwise, James, could you jump in and start with your presentation?
Certainly.
Yeah, then
Give it another 10 seconds or so, and then
yes,
maybe you can
that makes
have
sense.
me take over.
I make you the presenter and you can take over.
Yep.
And we give Mark the time to find a solution. All right, let's do that. I will make you the presenter and you take over, James.
Yep, sounds good.
Excellent. Thank you. Again, ladies and gentlemen, sorry for the inconvenience here. We are working on a solution.
All right. I trust everyone can see my screen here.
Yes, we can.
All right. So the search that Mark was setting up is this search, which I'm just going to open right now and show everyone. So Mark mapped the data. You see weight, sex. We have our required model variables here. We're just not going to use these available columns, these unmapped columns in the available columns container. In the control file, you'll see that these columns actually will have a drop statement, meaning that they're not used. And we'll go to the search setup. So where Mark was at, we had Advan2 and Advan4 selected, and we had enabled all of our covariates. So now I'm just going to set up the search space for the optional parameters that Mark was covering here. So the absorption, ALAG1, we'll search on that. We won't search on ALAG2, F1, or F2. You can see that since we've enabled covariates, I can select the Show All button, and you're welcome to collapse this container as well to give you a little bit more real estate for setting up the covariate effects on your parameters here. So you can see that clearance, or searching for a effective sex on clearance, effective weight on clearance, and you can toggle these options in many different ways individually, right? Setting their presence to either present or searched in terms of the relation, right? Exponential or linear in terms of the functional form of the covariate effect. The boundaries, as you could see, I set up, we have 0.1 here, 0.75. So initial estimates can be set individually, or there's global options if you want to set them all for across the board here. And we would do the same for Advan4, right? So we would set up our the parameters that we would want to include in the search space. ALAG1 is search, again in Advan4. We have our required model variables. One thing I didn't cover in Advan2 is how we can search for omegas. So you can see, just similar to the thetas, we have the option to set the omega presence, so either none, present, or searched, in which case here we're searching on random effects for all the thetas here. And then we would do the same for setting up covariates. So I'm going to go ahead and cover this just like we did for Advan4. So many different options, right? If you just wanted to do it quick and easy, you would just search over everything. But again, the more models that we run, or the more parameters that we include in the search space, the larger the search will become, the longer it will take, essentially. So we've defined some options in the search space. Now we can go to the template extras section. So here are some options that we would include in that template file that Mark showed in his presentation. Some things that you would certainly want to include as fixed in this template file, such as the sizes block addition, the S block and the Cove block. But it's also important that we add table statements to this template extras. So for those who are familiar with the expose package, we create an expose data object from a non-mem output folder. And this expose data object essentially wrangles all the non-mem output files and the table files that you've specified here and creates a nice structured object in R that we can use to generate goodness of fit plots and tables with just a very simple command. So you'll see more about that when we go into the reporter. So for these tables, right, these are all pretty standard. One thing I will note is, when you're adding table statements here, it's important that the actual, we're not actually extracting any parameters here for our tables, but certainly the parameter must exist. If you do put parameters in here, the parameter must exist in all of those candidate model files in the search space. So what I mean by that is you can't request ALAG2, for example, there as a parameter, or ALAG1 even, because in some models, right, ALAG1 will be included, and in other models it will not be included. And for those models where it's not included, if you do have your table statement there with ALAG1, the model will error out. But there's some nice shorthand notation, right? For our ADAs, we can use the ADAs 1 through last to always, output all the ADAs associated with that particular model. All right, so we set up our table statements. Now we can go to our sigmas. So this is our error model. We can define values for the additive, proportional error model, or the combined. The penalties is this is where we would actually change those those penalty values that get added to minus twice log likelihood that creates the resulting fitness value. So you could see here they're completely customizable. By default, we have values of 10 for the parameters, 100 for failing to converge, 100 for failing the covariance step. So certainly if you wanted, there was a question about parsimony earlier, if you wanted a more parsimonious model, you'd really increase these parameter values as the search, right, would be searching for a model that has less parameters in it, since simply the penalties would be increasing the overall fitness value for less parsimonious models. Post-processing, so this is where you would add in the options for your R script. We do have examples, which I'll show you after this setup. 4 examples in the Pirana online help, 2 of which actually use post-processing. I'm getting some feedback here. 2 examples which use post-processing, one Python script and one an R script, both with the penalty to capture Cmax between the simulated and observed data. So that's the value of the R script in those examples. And finally, we go to the model selection algorithm. So here you can see we have different algorithms to choose from. We're choosing GA here. You can see the Gaussian process, random forest, gradient boosted random trees, the exhaustive search, which would search or would run every single model in that search space, and then PSO, the particle swarm optimization. So you start, maybe one of our hosts, if you can put yourself on mute. I'm getting a little bit feedback. Thank you. Would specify the number of models in every generation. So this is the number of models that are randomly sampled in the search space at each generation, right? We have 5 generations here. So this is the machine learning search component. Now, what Mark mentioned in his presentation was we typically combine the machine learning search with this downhill step, right? So the downhill search is that local search that we actually, combine with the machine learning search that provides more robust results. And that downhill local search, we can actually run it at the end of the machine learning iterations. So in which case the final downhill search will be run after the 5 machine learning generations have completed. or we can run it periodically, meaning at some interval, right? So the downhill period step, if we set this to 2, that would mean at every single iteration, or excuse me, every 2 iterations, there will be a downhill search, right? So this is how you can kind of infuse a local search into the machine learning iterations. So ultimately, when you do this, it will take a little bit longer to run if you compare to just doing the machine learning search alone. But we've seen many times that this integrating the downhill step typically provides more robust results. And with each search, there's different options, right? So we have GA selected here, and you could see some options related to the GA setup, such as the number of models to carry over between generations, various options around the tournament selection, which is sort of the algorithm used by GA, and how to kind of drive the selection of candidate models between each iteration. But you're always welcome to just use the defaults. And with that, we would hit save. So I actually created this search already. I'm just going to just exit out of it. And I know Mark was going to run this and go over some of the results, but in the interest of time, I'm just going to show you essentially what you would, the operation that you would use. So simply you right-click, run search, and you would select your Darwin profile, which you would configure in settings. So this just different options around the path to NMFE. If you wanted to use different versions of NONMEM, you would just associate your non-MEM version with a Darwin profile. Then you would hit run. And when you hit run, you'll see some console output. I can show you that output here in a second, but in the interest of time, I want to show you what happens after you run and analyzing the results. So with this model completed, I'm going to just go ahead and show you some of the output, right? So we created this Darwin Search 01 folder that Pirana automatically creates when I select Run Search. You see we have this temp folder, which contains every single model in each iteration, right? So you can always open up the model file for a particular candidate model. But what's a little bit more effective is to just look at the key models. So the key models essentially is every time fitness improved, a model's fitness improved one iteration to the next, that's considered a key model. And here we have, it looks like 7 key models, right? All the way down to our final best model, which was found here. And NMFNSO1 is the name of the folder. And then you see the model output. So Pirana really provides a great structure to analyze your Darwin search output. So any one of those models, right, in temp, I can go into, I'm in the Darwin extension, so I change this to mod now. I can just select the model. You can view your parameter estimates right here, just like you would from traditional non-MEM kind of workflows. So that's just a little bit about exploring some of the output from a Darwin search. But the most effective way to explore this output is in the Darwin Reporter application. So with the model selected, you could see that the output folder is attached to my Darwin search model. I can select this hourglass button, and this hourglass will launch an application called Darwin Reporter. It's a little slow screen share here. So I'm going to hit run. All right. So what this is doing is it's creating an exposed data object for each one of those key models that we've seen. And now it's going to launch the Shiny application. It imports the data. All right. Some major overhead with webinar. So this what you'll see is a nice dashboard overview of the search. So you could see each one of these plots you can pop out. You could see mean fitness by each iteration, minimum fitness by each iteration. You could see the composition of fitness, of minimum fitness by each iteration with respect to the penalty breakdown. Right? So you can see, if you want to, we'll toggle these off. You can see how the objective function value decreased over time. Then we can see how the penalties also decreased over time as well until we had our final best model here at this last iteration. Each one of those key models, right, you can view here in the table. Select model file. You can view the non-mem control file that was executed for that model. Some information here, just an overview about the number of models total in that search space. Right, there were over 1 million given the options that we set up. And you can actually drill down and generate goodness of fit plots for each one of those key models. But before I do that, I'm going to just tag these existing plots that I showed you on the previous page, because I want to include these in a report, and you'll see what I'm doing with this tag button. Penalties versus iteration we'll do next. And there's also a table that you can generate. And all those plots and even this table are completely customizable, given options within the GUI here. If you want to rename, reorder columns, you can enter column names, drag them to different orders, select different columns that you want to include in your table. Tag this key models. Now for our goodness of fit plots, I can select this basic Goff node in the tree. And you can see CW-res versus PRED is selected. I could see the key model that I'm viewing that for right here. I could easily just change to a different key model or the final model and generate the same plot with the click of a button. I can tag this as well. So in terms of reporting on the search, right, you would want to tag your fitness versus iteration, penalties versus iteration, key models, maybe your residuals plots for some of your key models as well, and certainly the final best model. Let's say you have, we can do a DV versus IVAR too, DV versus PRED. All right, here's for the model 1. We'll tag the same plot for our final model. And for covariates, we can select the covariate model node. Here we're looking at ADAs versus sex. Tag that if we wanted to explore different covariate plots for continuous covariates, such as weight. Tag that. And finally, individual tables. If I wanted the overall table for a specific key model, I could select tables overall. You can see the overall, although most of this information is already included in our key models table. So maybe you'd want your theta table, for example, your parameter estimates. All right, let's tag the theta table for our model. And the act of tagging everything, if I go to the tag tab, I could see the underlying R code was actually generated for each one of these plots or tables. So this is very, very flexible in terms of any changes that I want to make in the GUI automatically get translated to the R code. But then I can even download a script, right, and make changes directly from command line if I want to reproduce the same plot. So with all those tag diagnostics, now I'm going to go to the report tab. We'll call this my report. I can select HTML, PDF, or docx output. I'm going to use auto formatting. You can see all my tag diagnostics. If I don't want to auto format, I can individually drop these into this container and arrange them however I'd wish. but we'll just use auto format. I'm going to hit download report. All right, should be finished any second. And for more information about this, I will just show you. You can access certara.github.io r/Darwin Reporter. So this is an R package that provides a Shiny application. You can also use it from the RStudio command line, but it has nice integration within Pirana as well. All right. It says my report has been saved to Pirana Report Shiny. So I'm just going to close this now, go back to Pirana. If I go to the Reports tab, the Shiny folder, I can see my report is right inside here. And I have a nice overview of that search. So it tells me the different penalty composition. We can see the fitness penalties versus iteration plot, which I showed. We tagged all these, so that's why they're included in the report. Our key models, you can see any goodness of fit plots or tables for the key models that I tagged would be included in here as well. You could see different section for the final model, goodness of fit plots. You could see we included this appendix, which includes all of our control files. So a lot of flexibility with what you can include in here, and the different outputs that you can generate directly from the GUI. But certainly, you can always download the raw R Markdown as well from that same interface if you want to make any changes, add any sections, any text to this report, or render it into different output format. And I know we're getting short on time, so the last thing I just briefly wanted to show you was with our final model in Pirana. So I can go to Key Models, right? Go to our final model. I'm going to change this to the mod selection. You can see this was our final model. So what I did was just duplicated this model for a VPC. I used final parameter estimates from that model, right? Which is this created the model with the final parameter estimates. I'm sure many of you are familiar with this functionality in Pirana. And then with this model, we just use PSN other, model diagnostics, VPC. So we won't have time to run this VPC, but I've already run it. And you can see that this VPC folder is attached to the final model. Now, just similar to what we did with Darwin Reporter, we can hit the hourglass. And you can see I have an option to run VPC results. If an estimation folder was attached, then we can run model results, which is essentially a similar interface as the goodness of fit plot and table generation that you saw in Darwin Reporter. But we'll run VPC results for this example. We're selecting the right VPC folder. I'm going to hit run. So what it's doing is it's importing from the M1 folder in the PSN VPC output, the observed data, which is the VPC original.dta, and the simulation data. And that's all that's needed for this interface. Once you have your observed and simulated data, we can launch the VPC results interface, which uses the tidy VPC package as a backend for the VPC parameterization and customization. I'm going to select DV for our yvar, time for our xvar, and simply plot. And I'll tag this just like I did in Darwin Reporter. If I included stratification variables in the PSN options, if I added the predcorrect flag, there's certainly different ways that we can stratify this VPC directly from the GUI. There's over a dozen different binning options available to you as well. Here we're using partition around medioids with 5 bins, including the binless method as well, which you can use. So a lot of flexibility with your VPC. You can customize this as well, any types of styling that you want to make. But from here, right, just like we had in the Darwin Reporter, we can generate the code for this VPC. You can see we're importing our observed and simulated data and then calling some tidy VPC and ggplot2 functions. And we can also generate a report. So we'll drag our VPC to the report output. my PC, download report. Right, again, just similar with Darwin Reporter, we can always download the raw R Markdown as well and render it within RStudio if we want to make any changes to the report, so we don't have to do it in the GUI here. And it should be finished any second. Go back to Pirana. All right. And we have a VPC, as you could see. So similar to the layout that we saw in Darwin Reporter. All right. I know we have a little time, so I'll just open it up to any final questions. Sorry for the technical difficulty earlier.
And I'm back if anyone has questions for me.
Yeah, thank you, James. It was a great presentation, great insights. We have many questions, great questions from the audience, and I'm not sure if it makes sense to start to work through these questions. What I can guarantee you, all the questions will be answered after the presentation. After the meeting, we will reach out to you individually to answer questions via email. I think that makes the most sense. For now, as James said, again, sorry for the inconvenience, for technical difficulties, but it was great input, and thank you for being an interactive audience today. And with that, I would wrap it up for today. Thank you to the presenters. Thank you, Mark. Thank you, James. And thank you to the audience. With that, take care and goodbye. Thank you,
everyone.